Hi, we continue chapter 4 and we give two results. First, the sandwich theorem that you already know for the sequences. In this context, it says that if you have three functions or three mappings, f, g, h, from I to r, and if these three functions satisfy f of x less than g of x less than h of x around a given point a, then if f of x and h of x tends to L when x tends to a, the same limit L, then g of x will tend to the same limit L when x tends to a. So be careful. It's not necessary to have f of x less than g of x less than h of x everywhere. It's only necessary to have this inequalities or this double inequality valid in a neighborhood of the point where I'm finding the limit, so in a neighborhood around a in this case. Also, we can prove that if we have two mappings f and g such that f of x is less than g of x for any x in a neighborhood of a point a, then the limit of f, if the limit of f is equal to infinity, so the smaller function, then the limit of the greater function g of x is equal to plus infinity as well. So you cannot have the smaller function going to plus infinity and the greater function going to a finite limit. We can also prove that applying some algebraic operations on the limits, we can find the limits of a combination of functions like sum of functions, product of functions, etc. So we have these six results. If f of x tends to L1, then the function given by the absolute value of f of x tends to the absolute value of L1. If f of x tends to L1 at a given point and g of x tends to L2 at the same given point, then f of x plus g of x tends to L1 plus L2. Also, if you have f of x that tends to L1, then if you multiply the function f by lambda, so you have the function lambda f, it will tend to lambda L1 at the given point. If f of x tends to 0 and g is bounded, then the product f times g tends to 0 as well. If f tends to L1 and g tends to L2, the product f times g, the function product f times g at the given point tends to L1 times L2, and also for the ratio. If g of x tends to L2 with L2 not equal to 0, then 1 over g of x tends to 1 over L2. And of course, we have also if f of x tends to L1, g of x tends to L2 at a given point, with L2 not equal to 0, then the ratio f over g tends to L1 over L2 when x tends to the given point. We had similar results when we were dealing with sequences. Let's try to prove some of the results given in here using the definition of the limit of a function. For the first one, for example, suppose that f of x tends to L1 when x tends to a, then using the definition of the limit, we have for all epsilon positive, there exists alpha positive such that if x minus a is less than alpha, then f of x minus L1 less than epsilon. To prove that the limit holds, or the absolute value of the limit is the limit of the absolute value of the function, then we need to prove that there exists alpha, whether it's the same alpha we had in here, the same alpha that exists in the first definition, or another alpha, such that the absolute value of f of x minus the absolute value of L1 is less than epsilon. So we know that the absolute value of f of x minus the absolute value of L1 is less than the absolute value of f of x minus L1 using inequalities given by the properties of the absolute value. So since we have this, then the absolute value of f of x minus the absolute value of L1 is of course less than epsilon for all x that belongs to the neighborhood already found around a, which confirms that if x satisfies x minus a less than alpha, so for the same alpha that we already found, so if x satisfies that, then f of x minus L1 in absolute value is less than epsilon, which leads to the fact that f of x tends to the absolute value of L1 as x tends to a. For the second property, for example, if you have two functions, f tending to L1 and g tending to L2 as x tends to the same point a, then using the definition of the limit, you have there exists alpha 1 such that for all x satisfying x minus a less than alpha 1, then f of x minus L1 is less than epsilon for whatever epsilon that you choose at the beginning. So what I will do here is that I will say that if you give me a number epsilon, I will take its half. So since the property is true for any number that I choose, I will take its half, and I will say that there exists alpha 1 such that for all x that satisfies x minus a less than alpha 1, f of x minus L1 is less than the half of the number that you gave me, so epsilon over 2. And also, since g of x also tends to L2, then I will take also the half of the number that you gave me, and I will find alpha 2 such that if x satisfies x minus a less than alpha 2, then g of x minus L2 is less than the half of the number that you gave me, so epsilon over 2. Now, taking alpha as the minimum, the least number between alpha 1 and alpha 2, then if x satisfies x minus a less than alpha, then x satisfies x minus a less than alpha 1 and x minus a less than alpha 2, because alpha is the least number between alpha 1 and alpha 2. So if x satisfies x minus a less than alpha, then these both inequalities hold. Therefore, we have the absolute value of f of x plus g of x minus L1 plus L2, which is the thing that should be less than the number that you gave me, epsilon, in order to have f of x plus g of x tending to L1 plus L2. So I take this, and then using the properties of the absolute value, I partition the absolute value in two parts, f of x minus L1 and then g of x minus L2, and I know that this first term in here is less than this second term in here. And then since these two properties are satisfied, then this is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, and I proved that we have L1 plus L2 a limit for f plus g when x tends to a. For the third property, it's a little bit the same reasoning, because you will give me an epsilon, and I would like to have at the end that lambda f minus lambda a less than epsilon. This is what I want to obtain at the end. Okay, so you will give me a number epsilon. I will use the fact that f of x tends to L1 to say that for any epsilon that you give me, I will divide this epsilon by lambda, and I will obtain a number. So for this number, there exists alpha such that for all x satisfying x minus a less than alpha, f x minus L1 is less than this number that I created, which is epsilon over lambda. It's true because this is true for any number that that I choose. So consequently, what I want to have is lambda f minus lambda L1. So I put lambda f of x minus lambda L1, and then I take lambda as a common factor. And since I know that this is satisfied for all x satisfying x minus a less than alpha, according to this, then this is less than lambda times 1 over lambda epsilon, which is equal to epsilon, the number that you chose at the beginning, which leads to the result. I will do also a similar reasoning when I'm multiplying a bounded function by a function that goes to 0. A bounded function g is a function that satisfies the following. There exists m positive such that there exists alpha 1. Of course, the function g in here is bounded in the neighborhood of a. It's not necessary that it's bounded everywhere. We should have at least bounded in the neighborhood of the point where I am calculating the limit. So there exists alpha 1 such that for all x in the neighborhood of a, we have g of x an absolute value less than m. So this is the definition of bounded in the neighborhood of a. F tending to 0 means that for all epsilon positive, there exists alpha satisfying such that for all x satisfying x minus a less than alpha 2, f of x minus less than epsilon over m. I take epsilon over n because at the end I will be multiplying by m in order to have epsilon at the end. So we choose alpha as the minimum between alpha 1 and alpha 2, so both properties are satisfied. Then if x minus a less than alpha, the product f times g is less than m from one side and epsilon over m from the other side. Simplifying m, I will obtain epsilon. So when you want to do such proof, you need to try to do it first on a scratch paper. Discover what number you should choose in here in order to have epsilon at the end when you multiply by m. If you do that, you will be able to find what's the number that you should be using here to obtain the good result at the end. Let's continue the proof of the other properties. In fact, in 5, 6, 7, I will be using the following. If f of x tends to L, this is equivalent to saying that f of x minus L tends to 0, using the first property. Because if you take L as the g of x, a function, the second property, the sum, then the sum of the functions f of x plus L or minus L will tend to the difference of the limits, which is 0. So in 5, I need to prove that if you have f tending to L1 and g tending to L2, then the product will tend to L1 times L2. So I need to prove equivalently that f of x times g of x minus L1 L2 tends to 0. Well, we know that f of x times g of x minus L1 L2 can be written as f of x times g of x minus L1g plus L1g minus L1 L2. So I added and subtracted the same term in here. Okay, why? Because I want to factorize and obtain the terms that I already know, or the terms that already satisfy some property. So if I take g of x as a common factor in the first two terms, I will have in here f of x minus L1 that I know that it tends to 0, and on the second part I will have g of x minus L2 that also I know that it tends to 0. And since I have a function that tends to 0 in here, and a function in here that is bounded in the neighborhood of A, because it's tending to a finite limit in the neighborhood of A, so it's bounded, of course. So since I have this product, a bounded function in the neighborhood of A times a function that goes to 0, then the product will tend to 0. Same thing in here. G of x minus L2 tends to 0, and L1 is a constant, it's bounded, then the product tends to 0. So we have all this that tends to 0, so f times g tends to L1 times L2. For the sixth property, it's a little bit tricky technical wise, but it's the same concept, of course. So if you have g of x that tends to L2, of course you have the absolute value of g of x that tends to the absolute value of L2. What we need to have is that if x satisfies x minus a less than a given alpha, then 1 over g of x minus 1 over L2 should be less than the epsilon that we choose, or should be something that tends to 0, right? So to prove that it's something that tends to 0, since it's positive, so it's greater than 0 from one side, we can prove that it's less than something that tends to 0. Then it will be tending to 0, of course. So I know that 1 over g of x minus 1 over L2 is less than 1 over L2 g of x times g of x minus L2. That's good, because g of x minus L2, I know that it tends to 0. So what I need to do now is to take this term and to prove that, I don't know, it might be bounded, or it can be less than a constant. Then I can apply the property that says that lambda g tends to the limit, the lambda times the limit. Okay, the property that we proved already. So I need to find an upper bound for this 1 over L2g. Of course, 1 over L2 is a constant, so I need to find an upper bound for g. I can say that g is bounded, or find the upper bound to say somehow that it's bounded. So to find an upper bound for 1 over g of x, I should find a lower bound of g of x. So this is the lower bound of g of x. So I will take epsilon, something that suits me. If I take epsilon as being L2, for example, this lower bound will be 0, and it will be problematic for the last inequality in here, because we have 1 over g. So I should not take it equals to L2. Let's take it half L2. it's true, the property is true for any epsilon. So if I take half L2 or 3/4 L2 or 2 L2 or whatever, okay, let's take half L2, then L2 minus epsilon will be half L2, and I will replace g of x in here by half L2, which will give a greater term in here. So I will have 2 over square root of L2 times g of x minus L2. So now we have this lambda times something that goes to 0. It will result in something that goes to 0, of course, as x tends to a. And for the 7th property, we will use the 5th and the 6th property, saying that f of x over g of x is a product of this one times this one, and we have the property for the product, which will give us the result. And we finish this part by this theorem, the theorem for the limit of a composite function. So if you have two functions, f going from I to r and g going from j to r, of course, to define the composite function, we should have f of I is included in j, so the images of the points in here should be something in here that is included in j in order to be able to define g at these points, because we need to define the g of f of x. So we should have f of I included in j. Then the composition of the functions f and g that I denote g round f, the composite function, is well defined by g round f going from I into r, because f will send it to fi, which is included in j, and then g will send it to r. It's defined as being g of f of x. Then, if you have a f of x that tends to a limit b as x tends to a, and g of x that tends to a limit L as y, or x in here, sorry, tends to b, which is the limit in here, then the limit of the composition g round f of x as x tends to a will be L. You are used to this result, you use it all the time without knowing, because when you calculate, for example, the limit of the square root of x, you take if x tends to a, you are putting a in here, and then you are calculating the square root of a. So you are calculating the composition, you are calculating the limit of the function inside, and then the function outside. If you take, for example, here f of x equal x, and g of x equals square root of x. So we are calculating, when you do this, you are calculating the limit of g round f using this result. To prove it, it's only sufficient to combine both definitions of the limits for both functions. So the limit of g will give us the following. For all epsilon positive, there exists beta such that I'm using y in here. So if y satisfies y minus b less than beta, then g of y minus L is less than epsilon. Also, since the limit of f when x tends to a is b, then there exists alpha such that if x satisfies x minus a less than alpha, then f of x minus b is less than beta. So again, what I'm doing in here, I'm saying that the limit of the function f allows us to write the definition of the limit of the function f, and the definition of the limit and the definition of the limit, we choose any number epsilon positive. So here we choose the beta that is in here. We choose the beta as being epsilon, and we say that for this beta there exists alpha such that f of x minus b is less than beta. And since f of x minus b is less than beta, then if y that satisfies this is the f of x in here, then since g of y minus L is less than epsilon, then g of f of x minus L will be less than epsilon, which will give the limit of the composite function. So this is how we prove it.